So in the last lecture I just started out on ways of devising linear field theory for bosonic fields, spin 0, spin 1 and spin 2, and I just indicated why when you go beyond spin 0, that is for spin 1 and spin 2, there is a natural reason in the linear limit for something like gauge invariance to emerge. The crucial point there, which I want to elaborate a little bit on because it is connected with one more aspect, is that when you start with say spin 0, you have something like you are thinking of an equation which is derived from a Lagrangian or an action which goes as integral over, let us say, d4x of some quantity like di phi with an interaction term which essentially is linear in phi, j times phi. Now when we take something like this and you end up getting an equation, you just have a 1 degree of freedom with box phi being equal to j. At the next level, when you want to have box ai or let us say a vi, some vector field, equal to ji, just the indices, Lorentz index structure tells you that the 9 Lagrangian which you would have written down, which is of the form dA VB dA VB, will require contraction on both A and B. So if you think of B as indicating which field, there are 4 such fields. For each one of them you are writing down this Lagrangian. You are absolutely assured that this equation will be taken care of. But because the signature is minus plus plus plus, you will find that there is a sign flip between the terms, as a result of which one of them will have wrong sign for the kinetic energy. We can arrange things in such a way that one of them has wrong sign in the kinetic energy. You eliminate it by saying that we need a gauge invariance in the theory, VA going to VA plus some dA of F. Okay. Then I pointed out that when you go to the next level, you will have something like dA of HAB times, HBC and a dA of HBZ, and the same problem will persist. And here the corresponding gauge transformation one thinks of is HAB going to HAB plus dA of psi b plus dB of psi. This arises just because of the way the indices has to be contracted and has to do with the sign. Now you may think it is a bit trivial and there may be ways of getting around it, but there aren't. And this also plays a very crucial role as to which of these spins attract and which of these spins repel. For example, let us look at electromagnetism. In electromagnetism, we know that like charges repel, while in gravity, like charges attract. And in spin 0 also like charges attract. And it alternates among these spins for the very same reason. So I want to indicate how that comes about. If you think of a theory like this, and you have 2 sources, let us look at scalar theory first. There are 2 source distributions, J1 of x and J2 of x. Yeah.
So, well, I said it the other week, but just to, as
you wanted to subtract out eta AB times phi for unimodal.
It's not a possibility. You can, if you assume this, you can also get a Lagrangian with only 2 polarizations at the free level, which is equivalent to linearizing unimodal gravity.
Yes, that's correct. But I told you that I don't like unimodal.
It's okay, but at the level of free fields, it's...
yeah, it depends on how much you want to subtract out. And I want to stop the subtraction at this level.
Yeah,
so that's a choice.
For electromagnetism, let's say that there is only one possibility for the gauge.
That's correct. Here there is more possibility. That is because for spin 2 there is both vector and scalar, which is subcombinant in the Lorentz group. While in the electromagnetism there is only a scalar. So that is fine. Yeah.
Can I add another point?
Yeah.
Your series HAB is symmetric.
Yes.
Anti-symmetric.
Now there is a reason for that. You can add an antisymmetric HAB and look at that structure. It becomes much more complex. Now, I am trying to motivate this whole thing towards gravity. Okay? So ultimately I wanted to argue that you cannot start with a gravitron theory because there is all kinds of confusing statements in the literature. And for example, one of the main particle physics statements, which happens to be not quite true, is that you can start with a graviton Lagrangian and iterate further and get Einstein Lagrangian, etc., etc. So I want to make a lot of statements about that. So I'm going to confine myself consciously to things which are closely related to gravity, where this HAB eventually is going to be the spin 2 field. And I'm going to construct before your eyes the Lagrangian for the spin 2 field, just using symmetry, and then ask whether we can go from there to Einstein gravity, how much you can go, what you can do and what you cannot do. So that is the broad motivation. That is why I'm throwing away the antisymmetric part.
In string theory, you do have both.
That's correct. That's correct. That's correct. So this is.
You have GR as the limit.
Yeah, as long as you have a HAB, then you are fine. But the question is whether you want to add more structure to it, like a scalar degree of freedom, an antisymmetric tensor degree of freedom, etc. So I am taking the minimalistic approach and just looking at the canonical spin 2 second rank symmetric tensor field. Okay, fine.
So there should be the couple. When if they interact at the tree level, there is also ghosts.
Yeah. Yes, but I'm not going to do any of that because this will keep life very simple and it will serve our purpose. Okay? And I will build for you Einstein theory in a particular way. Okay, so you have this much of invariance up to this point. I was commenting on the relationship between the contraction of the Lorentz indices and whether something attracts or repels. The point is that if I have two sources, J1 of x and J2 of x, you ask what is the interaction energy between these sources. So there is a J1 of x which produces a field phi and then it couples to J2 of x. And let us think of the static situation. Then you can immediately write down in the first case that the interaction energy in the static limit will be something like an integral over, let us say, d3x, d3y of some j at x, j at y times a g of x comma y, which is your standard Green's function. For a massless case, it is just 1 upon x minus y, the mod square. So this is the interaction energy. And if you write down the corresponding thing in the vector theory, you will end up getting the same kind of integrals here. And here you will get a J0 contracted with another J0 times a G00. That I will just denote by G. That really doesn't matter. That is, I am thinking of a source in electromagnetism where only the zeroth component is non-zero. So think of your del square phi is equal to rho electrostatics 101. So I have a charge distribution and I am looking at the energy of that charge distribution when it interacts with another one. I could have put 1 here and 2 here. Two different distributions. So this is also 1 here and 2 different distributions. But the crucial difference here is that one is down and one is up, the indices wise. And that essentially comes when you do the proper contractions with the G00. There will be JA, JB times a GAB, and when you do the contraction, this is the structure which emerges. Now you have to rise or lower one of them, so which you don't have to do here. So with this signature, it is very clear that if everything else is the same, there is an extra minus sign here. When you go to the gravity, the same thing will give. It is actually going to be more complicated and we will work it out. But if only T00 or J00 as I am indicating here, some kind of a source like this is non-zero, you will have a structure like this. But now we are back to square one because you are rising two zero indices. So it actually nicely alternates, which again has to do with this Lorentz symmetry. And this is why a vector field, essentially, once you normalize everything with a vector field giving you the like charges repel kind of procedure, scalar will attract and the spin 2 will also attract. Okay? Fine. Now having made this preliminary comment, let us now go ahead and try to construct these theories.
So yeah. If I choose the convention plus minus minus minus.
Okay. If you choose that convention, life is much more difficult. It turns out that the conclusion, as you can expect, is still true. But the extra signs which you have to throw in here compensates for that. I think it is described in the notes. I have made a comment as to what happens. But life is a lot easier when you use minus plus plus plus. Okay. Right. Now, I want to construct these actions for you. I will briefly mention this electromagnetic action business in order to motivate how I am going to do that. Because that is trivial, everybody knows what we are going to get. And then I will spend time constructing the action for the HAB field. So what we want to do is to write down an action for the field, for the vector field, which I am going to write as some integral over d4x, flat space-time, quadratic in the derivatives of the field. So typically I have a structure like some m AB ij dA of AB. Now I switch to the standard vector potential notation, di of aj. This is the generic quadratic term I can write down for this vector field. The question is, what is ABIJ is going to be? It has to be built out of the only tensors which are available to you, which are, because we want the theory to be linear, one is epsilon ABIJ. This is available to you. Then you have eta LM, Lorentz space metric, which is available to you. So what are the terms which you can write down? So the terms you can write down here will have first, let me write down each of the terms. First will be epsilon ABIJ dA of AB dI of AJ. This is possible. Then you want to think of how many ways you can contract these indices. There are constants in front, and these are going to be product of two etas, which essentially tells you how many ways you can contract that. So if I contract the A with I get the term dA AB. It's some constant here. Or I can contract A with B itself. So I have another term, which is C2 di of AR whole square. These are the only two possibilities. This A can either contract with itself or it can contract with this. Okay, or I can write down the third one, which is C3. There is one more possibility, dA of AB and dB of A. Okay, it's just a reverse of this with a B and this thing. Yeah.
So it cannot be in 4 space-time dimensions.
Then there are more possibilities. I'm going to stick to 4 space-time. That also I can discuss. But again, as I said, this talk is geared towards something which I want to do. So I'm just sticking with that. In fact, electromagnetic structure in 2 and 3 dimensions are more interesting in some way. So is gravity. But I'm going to stick to. So these are the possibilities which you have, and which you can just write down fairly trivially, and you will find that it is much more complicated when I go to HAB, and this is a warm-up towards that. Then what you do is that you ask which of these terms can be gauge invariant. I'm not even going to work it out because we already know the answer. Okay? The easiest way is to separate this out into a symmetric part and an anti-symmetric part, and you know that the anti-symmetric part is anyway gauge invariant and symmetric part cannot be. So when you work that out, you will find that these coefficients has to have specific values. The gauge invariance of the action uniquely determines the form of the Lagrangian, and you will end up getting the first term you will not be able to do anything about. So you will have EAB IJ dA of AB di of AJ. This is gauge invariant. Then you will get your usual some constant times Fik. So the idea is to write this down, make the gauge transformation, and say that all the gauge dependent terms just vanish, and that will give you conditions on C1, C2 and C3. You can throw in those conditions and you will find that this is the only possibility. So it is done in the notes and I will leave it you to work that. What about this term? I want to spend a moment on that because that is not sometimes discussed. So what does that tell you? So the term which we have, that extra term, first of all, since these are all antisymmetric, I can pull these indices out. That is going to contribute for you in the action an integral over d4x of dA of E AB ij AB di of A. So this is what it will contribute in the action, and we are interested in two hypersurfaces and we are looking at a t is equal to constant hypersurface. So this will go on a t is equal to constant hypersurface. When you do the integration by use the Gauss theorem, you will get an integral over d3x. This is 0. So epsilon 0. That means this has to be special coordinates. Alpha, beta, gamma. A alpha d beta of A gamma. Further, this is antisymmetric in beta and gamma, so this can be replaced except for a factor which we are anyway ignoring, F beta gamma. Now, F beta gamma contracted with epsilon 0 alpha beta gamma is essentially going to give you the magnetic field. So this is going to have a structure which is integral d3x A dot B. This goes with various names. It is sometimes called Chern-Simon term in a different context, but it is essentially the same structure. It is also called magnetic helicity in plasma physics. In plasma physics, it plays a crucial role where you think of this B as curl of A and A dot curl of A, and it's called magnetic helicity. But for our purpose, when you look at the variation of this term, this is a surface term, but I have been trying to sing the song all along that surface terms are important and you cannot ignore them without looking at it. That is the spirit in which it is being looked at. When you look at the variation of that, this is fine because delta A alpha will vanish on the surface. We keep A alpha fixed. Here there are only spatial derivatives. Therefore, this is also fine. Because if I am fixing the vector potential all over a surface, there are derivatives along this surface. The spatial derivatives are also fixed. Therefore, there are no variations which contribute from that. It is because of that that you can throw away this in standard electrodynamics. Okay, so this goes and you end up getting this term. Okay. Now let us play this game for HA. So I want to do the same thing for the case of a, let's say, weak gravitational field or a spin-2 field or whatever. So what is the action I want to write? So I want to think of an action, except for constants again, an integral over d4x. Now there are more indices, so it is m, abc, ijk, dA of hbc contracted with di of hj. Question is, what are the possible combinations which are allowed here? So I'll try to do this with some detail, but at some stage I will say rest of it you follow from the notes. It turns out to be reasonably non-trivial. Now you need a 6-index object, again constructed out of epsilons and etas. So obviously you can have 4 indices from epsilon and 2 indices from eta, and you can convince yourself immediately that they will all vanish. Because if you want to pick 4 indices, you have to pick a pair out of this, which means that when you work out the symmetries of the theory, they will all vanish. So it has to be built out of etas. So if you take etas, every eta is going to do a contraction here. So for counting purposes, it is better to write it down in terms of that. So I will indicate, for example, let us take the simplest, suppose I take A and I contract it with I. So I have AI, then I contract B and C, so that will be BC, and then JK. By this symbol, I mean that I am writing down a term in which A is contracted with I, B is contracted with J, B is contracted with C, and J is contracted with K. This is one possible term. Okay, you put the corresponding agents. Once A is contracted with I, B can either contract with C, or it can contract with J or K, but they are the same, so we'll just pick one of them. So you can do AI, BJ, CK. This is possible. Okay? Now let us take A and say that it is contracting with B. So I have AB. When I take AB, C can contract with I, so I have CI, JK. And similarly, I can have AB, CJ, IK. So I have AB, C has been contracted with I, and C has been contracted with J. Okay? So these are the only two possibilities there. Then we have A, which let me contract with K. So I have AK. Once I have AK, then B can be contracted with C. And I have a BCIJ. Then I can have AK, BI, or BJCI, BJCI. Then I have AKBICJ, AKBICJ. That is also a possibility. So let us work through this. A and K has been contracted, but B's contraction with either C or I or J are all different. So this is, all of them has to be listed down. So I have a total of 7 possibilities here. And now the question is, which of them I can eliminate by symmetry arguments, etc. Okay. So out of this, okay, let me start with, for example, this one. You look at this term, and you notice that the entire structure has a symmetry under ABC going into IJK, because it is symmetric on the reversal. So if I take, assuming I am doing it right, otherwise I'll go back to my notes. So let us take ABC, that will become IJK, I will become A, then B, and C. And let us see whether we have anything which looks like that here. So this is whether it is AK contraction or KA contraction is the same. So look at the set of AK contractions which we have. There is an AK, BC, IJ. Fine. So I can retain this and throw this out. Okay. Then I have another term. Let us look at these two. And then it is easier to do it in one direction. So let me get it right. Yeah. So you take this and you again do the same transformation. So this A becomes I, K becomes C, A, B, C is I, J, K, and B becomes, okay, this is G and B just get reversed, and I becomes A. Okay. Now, this is almost quite close to this, and you have to notice that the whole thing is also symmetric under BC, because I can reverse B and C. So this could also be written as IB, JC, AK, and we have a IB, JC, AK here. Okay. So I only need to retain one of them, and I think I retain the last one. So I throw this out, and I retain this. Okay. So we have started with 7 terms, brought it down to 5. Now there is one more symmetry which we have not used, And that comes into play to eliminate this term. And that is a little, again, a bit non-trivial, and that is going to play a crucial role when we generalize it to GR, or attempt to generalize it to GR. Let us look at any one of these terms, in particular this term, that has a structure which is like something with, let me just write it down, M, A, B, C, I, J, K, D, A, okay, I won't even put the contractions. Let me just look at this structure which is there itself, and let me pull out an A. So I write it as dA of HBC di of HJK. This is fine because these are just constants and I can pull it through. What I wanted to argue is that suppose I think of this A acting on this term. It will become symmetric in A and I, and at that time I can flip A and I. Now if you take another term which had this I and I pull it through, I can again flip that. Which means that from the structure of this, we know that you can interchange A and I. This is not coming out of the symmetry, this is coming at the expense of a surface term. So let us make sure we understand that. If I take this term and I think of this as a total divergence, okay, and then you take this, go into this, take this derivative, operate on this, I will pick up a AI. Then you take the same term, which we know is equal to this, and then do the same thing with pulling out I. So you have two surface terms which are different, but they are both surface terms, and the derivatives are going to act on AI or IA. Therefore, that can be flipped to each other. So except for surface term, you can flip this. Okay? And in conventional high energy physics, surface terms are completely ignored. So using that surface term, we will be able to eliminate this term. So let us see how. You start with this, and you first interchange those two. Then you end up getting I, B, C, J, A, K. Now again you come back to our AK terms. So I have an AK, CJ, BI term, which I am anyway retaining. So this is equivalent to this except for a surface term. So we are going to throw this away, saying plus surface term, which we are going to ignore for the moment. I will come back to this. So you are finally left with just four terms. These two which we did nothing, and this we did all the elimination. Okay. Now you write down the expression for this with each one of them appearing with eta. And then you play the same game. You say that HAB going to HAB plus DA psi B plus DB psi A should be an invariant solution. Remarkably enough, it allows you to fix all the coefficients, just as it happened in the electromagnetic. And if you do that, the final structure of MABCD which you get is the following. You find that M, ABC, IJK has the following structure, which is eta AI coming from the first terms, but with eta BC, eta JK, this is the very first term, and the other term comes with a minus sign, which is eta BJ, eta CK. Then you get a term which is the other two with a factor 2, eta AK, which is common in both. Then you get a eta BC, eta IJ minus eta BI, eta Ct. Okay. So just from symmetry, let me just summarize what we have done. It is actually an interesting achievement, originally done by Fieris and Pauli. They didn't exactly use the same motivation as ours, but they got this. If you want to look at the most general Lagrangian, quadratic Lagrangian, involving the derivatives of a second rank symmetric tensor field, this is what you will write down. Where this m should depend on etas. It should have 3 etas in it. Now, you use first of all whatever is in your hand, which are regular symmetries, by which you can eliminate out of 7 possibilities 2. So that leaves you with 5 terms. At that level, you cannot determine all the coefficients of the 5 terms. But you can use the fact that one of those terms can be transformed to the other except for a surface term. And if you throw away the surface term, it reduces down to 4 coefficients. So you write down the most general expression involving these 4 coefficients, which would be this, 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 and this. And then you impose gauge invariance. That is the most important part. You impose the gauge invariance on your minimal structure, and you find that except for the surface term which you have thrown away, the action has a unique form. So the action, I can now immediately write it down. I just have to take this and multiply with this, and I will get exactly the contractions which I need. Okay, and it has very specific coefficient system. Yes.
If you would have imposed the gauge invariance before,
Yes.
then those derivatives would have been covariant derivatives. I mean, it's not true that they commute. So you would get...
I'm going to come to that. There are lots of interesting things which happens, and it doesn't go into covariant derivative, etc. I'm going to spend quite a bit of time on that. Okay, so just hold on for a while. Yeah. So this is the structure which emerges. So first, let us forget everything else which we know. We are just looking at Lorentz group structure in flat space time in Cartesian coordinates. We are not even going to go into curvilinear coordinates. In the Cartesian coordinates, we want to write down a theory for a spin tube symmetric field, which has a particular gauge invariance. Okay, so then that we have achieved. This is the kind of thing which you can have. Now as I said, there are several comments which I want to make here. First of all, how does that action look? Well, I can write it down. It is a mile-long expression. It doesn't illuminate much. But we will need some of those properties later, so I will write it in a sort of reduced form. In the reduced form, when you write this whole thing, the action will be proportional to the following term. Integral d4x. This is not too difficult to arrive at. dA of het bb and a dA of het jk. Not quite, there is a bar on het which I will explain to you in a minute. Then minus dA of het bc with a bar and a dA of HBC with a bar plus 2 times dA of H. This should be contraction, should be, this is fine, so this should be A of HBC, the C of HB, where this quantity H bar of AB is defined as HAB minus half eta AB a trace of H. Things are simpler in terms of this combination, and this is the action. Okay, so you just have 3 terms. Yeah.
This last H, the first term should be on the.
Let's see. dA of H bar
the
B.
one on the left.
This one.
No, on
The contraction of the...
yeah.
Correct. That's it. Okay. Thanks. So this is the structure which emerges, and there are several curious things which happens with this structure which I am going to mention. But I want to first tell you something else. Let us now do the following. We have the action which has been obtained, and this has been a flat space-time action for a spin tube field. So let us sneakily do the following thing. We know that eventually we are interested in Einstein's theory with a metric GAB and whatnot. And this HABs which I am working with, just to make things clear, are canonical fields. And fields have dimensions of 1 by n, all fields in natural units. That is, the actions in quantum field theory would be quadratic in the first derivatives, integrated over d4x. The quadratic in the derivative gives you 2 factors of length in the denominator. So the field should have dimensions of 1 by n. So what one is thinking of eventually is something like GAB, which hopefully will be obtainable as some eta AB plus some length HAB. Okay? So this will turn out to be proportional to Planck scale and things like that. Okay? So this is what one has in mind. With this in mind, let us take that action which we have written down, which is of the form integral d4x m abc ijk dA of hbc di of hjk. Okay. Where this m is built out of etas, 3 etas. Then I am going to do the following. I am first going to replace this d4x by root minus d d4x. This is pure kinematics, because if I write down the same equation and I want to think of this spin 2 field in spherical harmonic expansion, I will use polar coordinates. And I won't write dr d theta d phi, I will write r square sine theta d theta d phi. Okay? So this is pure kinematics, no one should object to that. Then since this eta AB has 0 covariant derivative, presumably I am also allowed to, okay, there is some this HAB with this L factor coming in. So I will replace this to dA of GBC di of GJK times n 1 by L square. Again, no one should object to that, because I can just think of it as my definition. I can define a quantity GAB of x as eta AB plus this quantity. Therefore, this is fine. The really objectionable thing I am going to do is to take this, and wherever I see m, I am going to replace it by g. I have no justification for that, I just want to do it. Okay? Now I obtain an action. Yeah.
How about derivatives?
Ordinary derivatives, no covariant derivatives. I'll come to that. Okay? Suppose I write it down like this. What do I have? I now have an action which looks like integral d4x root minus g. There are terms here which involves g, 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 products of 3 g's with some specific form. Then I have a dg square and I have an 1 by L square. Believe it or not, this happens to be the exact action in general relativity. That is, if you take the exact Einstein-Hilbert action in general relativity and throw away the surface term, so that you get the square of the gammas, which we wrote down at another day. Square of the gammas will involve squares of the first derivatives of the metric multiplied by a set of metric, and this will identically match. Now I want to spend some time convincing you that this is a deep mystery. Nobody knows why this works. Now, the first thing which you will say, oh, come on, this is just principle of equivalence. Principle of equivalence tells you that in a local region, Eta is like G, you go to a local region where there is a Lagrangian and there is an eta and then there is a G, and you replace every eta by G. Okay? After all, this is a tensorial expression in the local special relativistic sense, and you replace it by G. And of course, Winslow-Hyginus also tells you that d4x should be replaced by root minus G d4x. So what is the big deal? And here derivatives don't matter anymore. The big deal is exactly what has been bothering many of you, the derivatives. Okay. Now let us, in order to put it in perspective, let us think of it in a slightly different way. Suppose someone has given you this theory and you know nothing about general relativity. You are trying to build a theory for gravity, a Lorentz invariant theory for gravity. Then you think maybe HBZ is a good choice, so you are exploring that. Now once this theory has been given, suppose somebody says, I actually want to do YL and theta phi expansion for this, I want to study spherical waves of the spin 2 field. Okay, spherical tensor harmonics or some such. Then what would you have done? What Lagrangian would you have written? You would have written down exactly this kind of a Lagrangian with these things replaced by covariant derivatives. Because you are after all working on spherical polar coordinates and you can't live with ordinary derivatives, you will put covariant derivatives. So you will have covariant derivatives of that. You cannot put covariant derivatives here, that is obvious, they are zero. Covariant derivative of metric vanishes on you. Okay? Now, the reason is that if you take a covariant derivative of this, covariant derivatives of etas are not zero. Because when you take covariant derivative, you have the ordinary derivative plus gammas. Then of course you impose your usual symmetry conditions and then they vanish. So whenever you have a covariant derivative coming out of a connection which is compatible with the metric, you have no go here. So you have to somehow say that I will leave these as ordinary derivatives and allow me to change everything else. And that does not have a real justification. At least once you know the answer, you can justify yourself. Until you realize that we did a swindle in getting this action in the first place. We threw away surface term. Okay? So you go back. You go back and say, suppose I didn't throw away that surface term and I had kept it. Okay? And what would happen? Would it have produced for me the standard surface term? No. It doesn't produce anything which you know of. It's a horribly complicated object and it is there in one of my papers. You can look at that. It doesn't have any simple geometry. So you have to make a very specific choice in order to get this. There is actually more trouble in store. When I had this list of terms, I had a note here in which I carefully kept when two of them are the same, what I retain and what I throw away. I mean, instead of crossing this out and retaining this, suppose I had done it the other way around. Again, you will find that they differ by covariant derivatives. And this is the point we were making. So then you will find that you end up getting a theory which is nothing like general relativity. You will get a much more complicated theory. So what one can show is that there is a particular choice of surface terms to throw away, after which you get this structure, and then you quietly replace it like this, you end up getting general relativity. I think this is since most of these lectures are intended to graduate students, I think there is something interesting here to be explored. I have spent quite a bit of time and written one long paper in it, but I don't quite understand it. There is something mysterious about why this works, even with a particular choice, which I don't quite know. There may be something, but this is the fact of life that with a specific choice you can do. Of course you can, yeah.
I may comment that of course those other terms can be built up to produce
General relativity.
plus terms that are like R squared.
No, actually you cannot. And that is what I'm going to spend quite a bit of time. What you can and what you cannot. There are statements in the literature which claim various things. But most of them sneaks in extra assumptions when you are not watching. So I'm going to spend a bit of the time doing that next. Yeah.
So what happens if you keep the H there, but you replace the D with covariant derivative?
Yes, you can do that. Okay. Then you end up getting a very interesting theory which has nothing to do with GS. Okay. This I have sort of explored in that paper, showing what coupling it gives to TAB and things like that, but it is not GR. That would have been if you knew nothing about GR and you are working in 1910 and you knew Lorentz group structure, that is the theory you would have ended up with. Yeah, it will be Lorentz invariant, yes.
So what is it, that theory?
Oh, it is just a theory with some tensor field coupled to matter in a very crazy way. Okay, there is some source, etc. It will take me too far away to discuss that, but I can talk to you about that and I can give you the reference. It is there in a paper, I worked it out. But it is not a very interesting theory, and it has nothing to do with GRN. It is in fact an ugly theory. So, but you can look it up, I mean, what you will get. Okay, but there is something which you can do in the reverse engineering direction. Suppose you have been given Einstein's theory, then everything is fine. You start with Einstein's theory, you plug this in, and you linearize. Then you will end up from the quadratic path this time. Okay? And in fact, that is what you would do if you are working in, for example, gravitational waves. In fact, you will do something more general because you may want gravitational waves propagating in a curved spacetime. So you will start with some background, but right now let us think of gravitational waves in flat spacetime. So you linearize around the flat spacetime and you look at these quantities, and this equation which I have written down, or this action, describes for you the dynamics of the gravitational waves. If you vary that, you will get a field equation which will tell you how gravitational waves are produced, etc., in the linear limit of the theory. However, there is a catch even in this. When you look at Einstein's theory, you will find that there are two pieces. There is one piece which gives you the bulk term, and one piece which gives you the surface term. And I spent a lot of time on the surface term in the previous lectures. It turns out that the surface term is non-analytic in the coupling constant. It is not a fact which is often appreciated, so I am going to spend a little bit of time on that. First of all, if you take the Einstein's theory and you linearize it, the bulk term, which has gamma square, will lead to this. What does the surface term lead to? Surface term leads to the following quantity, which I will write down. The surface action in Einstein-Hilbert term, again, forget constants for today's talk, d4x dA dB of HAB minus eta AB H. H is the trace of HA. Yeah, I think that is what it gets. That's correct. Because this is first derivative of the metric that gives you Christoffel symbols, and this is the divergence of the Christoffel symbol. Okay? Now this has several interesting properties. The first point is that this term happens to be gauge invariant, this entire term. So just to see that, if I take HAB and you change it into HAB plus dA of psi B plus dB of psi A.
Sorry, confused. Why is it linear in H?
Because I am linearizing it. Oh, okay. What I said was, suppose I start with the... Sorry. It is not quadratic. That is the point. You see, if you look at Einstein's theory, Einstein-Hilbert action, this was done in a previous lecture. Essentially what happens is that you have a root minus d d4x of r, which you write as d gamma plus gamma square. Right? The standard separation of r. This gamma square times this is what I call a bulk. This will be quadratic in gammas. Then you get a term which is of the structure integral d4x d of gamma. This is the surface term which you usually throw away and you never look at it. And that is what I did spend some time in the previous lecture, so I am coming back to this. This holds no surprises. If you linearize this, you get back exactly this. So that is fine. And that is where you vary and you do your actions and all that sort of thing. I want to concentrate on this because it has very interesting properties. So that leads to this quantity. Now let us look at how it changes under gauge transformation. So this is how HAB will go, and H will go to H plus dA psi A with a factor 2. Now if you plug it into this and you look at the derivative structure, this dA dB acting on this is essentially going to give a box of divergence of B. Okay, because you can commute ordinary derivatives. you will get another box of divergence of B here. So you get 2 times box of divergence of psi from this term. In this you will get again a box of H, and that is box of divergence of. Therefore, we know that this term is gauge invariant. Now this demolishes another myth which is usually prevalent in high energy physics community, that gauge transformations of a spin 2 field become general coordinate transformations in the full case. They do nothing of that kind. And this is very important to understand, because normal intuition in high energy classical physics comes from Yang-Mills fields. In any gauge group, standard Lie group, which mathematicians will be very precise, we were discussing it over lunch, any well-defined Lie group, if you know the way the group operates near the identity, there is a way of exponentiating it and getting the finite changes. So if you are looking at a gauge theory, and if you know how things change close to identity, except for sectors which are not connected and that sort of problems, usually if you ignore topological structures, then if you know what is happening near the identity, the connected part of the gauge group can all be obtained by exponential. So this makes you think along the following line. Well, xa to arbitrary functions of xa is a group, of course, it's general coordinate transformation group. The infinitesimal part of it is xa going to xa plus xia. When xa goes to xa plus xia, I know that the metric changes by precisely this part. So if I had added an eta ab here and an eta ab here and think of that as my metric, the part eta ab remains invariant and my spin 2 field changes like this. Therefore, the linearized coordinate transformations are the same as gauge transformations of the linear theory of a spin 2 field. Perfectly correct statement, nothing wrong. The converse is not true. Okay? The converse is, suppose I have a term which is gauge invariant in the linear theory, then there is some way of exponentiating it and obtaining a generally covariant terms in the full theory. So this is an explicit counterexample, because we know what this term is. In fact, we wrote it down the other day. It was dc of root minus g vc with vc given by that horrible expression minus 1 by g dA g gbc. You can easily convince yourself that this is not generally covariant. It doesn't require much of a demonstration. Then you should go and linearize it, and you will get this. So this is an example of a term which is not generally covariant under arbitrary coordinate transformation, but remain in gauge invariant under gauge transformations. So that is the first non-trivial feature about this theory. Second, we gave a very simple physical interpretation for this surface term. I showed you the other day that in any space-time with a horizon, where the near horizon structure has a Rindler kind of a metric, then if you evaluate the surface term on the horizon, you get the entropy of the thing, entropy of the horizon. Now this, I told you, goes much beyond Einstein theory. This is true for all examples which is known to us. Like if you take Lovelock Lagrangians, f of r gravity, in almost all the theories where you suitably defining this term, in Lovelock theories it is very clear and very easy to see. The surface term gives you the entropy of the event horizons of the black holes in the theory, or any generic event horizon if you think of local observers. And I explained to you why I believe this is a very natural thing, etc., etc. Now you can ask the question, what is black hole entropy in terms of gravitons or the linear spin 2 field? It doesn't exist. There are various reasons for saying this. And one simple way is that you cannot evaluate this quantity the way we did it that time. In order to do that, we had to very crucially use a non-perturbative feature of the theory. We wanted to take a metric. Let me just remind you what we did that time. Like this. what we did that day was to take a metric which near horizon has the form minus kappa square x square dt square plus the spatial coordinate, the Rendler form. Then we said that you can go to the Euclidean sector of this theory, which is dt e square, which becomes an angular coordinate. And then we evaluated everything on the Euclidean sector. That is, we took this space-time, which is x, t, this is g or kappa te, x, and we took a surface here at some radius epsilon. This is the horizon in the Euclidean theory. So we took a surface of epsilon, then we evaluate the surface time on this and took epsilon going to 0. All these requires you to be able to describe something like this. That is, you have a G00, which is kappa square x square, plus or minus depending on whether you are working in Euclidean or in the real. This can never come out of 1 plus some h00, which h00 being small. You cannot make this quantity vanish in a linear approximation. It's a very trivial comment in some sense, that if you are going to linearize the theory, after all you are taking eta AB plus some HAB and you cannot make the eta AB wiped out by the HAB because HAB is supposed to be small. Yeah.
Well, could you do it if you went to a different background and linearized around it?
Yes, one can try that. Then what you will find is that the entropy contribution comes entirely from the background, and this makes no contribution even in the curvature system. So in that sense, it is a non-perturbative feature and you cannot get it out of this. Now the mystery actually gets a little deeper when you look at how the scaling with respect to L goes, which we have not looked at yet. And that is very easy to see, but I will explicitly write it down. See, what we have, if you look at the Lagrangian for Einstein theory, just formally, it has a structure which goes as dg the whole square plus d square g, right? Because there is one term which is quadratic and one second derivative term, and the whole thing is multiplied by 1 upon some length square. It is 1 upon 16 pi g and g h cross upon c cubed, which is going to give you the Planck length square. Now what you are going to do is to say that g goes as eta plus LH. And you plug it into this. What happens? Your L will become, so here dg only picks up contribution from that. That L square will cancel this. So let me write it down explicitly. So you have L square dh the whole square. Then I have a d square g, which is going to be L d square h. The whole thing is multiplied by 1 by 8. So this is going to go as dh the whole square plus 1 by L d square h. This is such an elementary scaling that there is no escape from it. Okay? But it has a deep significance. What it tells you is that treated as a perturbation around flat space-time with HAB describing the canonical graviton field with the correct dimension, arranged in such a way that the leading term is precisely what you want for a spin 2 field, what we originally derived. The surface term is non-analytic in the coupling constant. Okay, it has a non-bias. And this is the same as what he was commenting, that this term is linear in H. So there is a quadratic term, which is what gives you the dynamics, and then there is a surface term which is linear in H. And when you do the scaling, this is the way the scaling. This is a more nicer way of presenting it in terms of canonical dimensions. Now why is it so important? Its importance, yeah.
Can you repeat why it's linear?
Yeah. So if you look at the structure for Lagrangian, now we are going reverse engineering. You start with the Einstein-Hilbert-Lagrangian. Einstein-Hilbert-Lagrangian has an 1 upon 16 pi g, which I have written as 1 upon L square with the correct dimensions in natural units. Then there is one quadratic term in the first derivatives of the metric, which is del g the whole square. Then there is a term which involves second derivatives of the metric. Now, in the canonical spin 2,
But it also has inverse metrics, no?
that doesn't make any difference, because all inverses will go with etas to the lowest order. Okay, so when you, and in fact you can do it more rigorously, and you will end up getting this with an 1 by L in front. This is what you will get. Which again you can fix with dimensions, because this has dimensions of 1 by L, this has 2 dimensions, so there must be an 1 by L there.
Yeah, the question was why is there just one H?
Yeah, that is because there is only one g in the second derivative term. It is linear in the metric.
Yes, but I thought the inverse will also be something.
That will go away, because to the lowest order it will not contribute. Yeah, but we did that in the previous lecture.
Yeah, okay.
Yeah, right. So that is very straightforward algebra, but its implications are what is non-trivial. I mean, this part nobody will recall. The place where the quarrel arises is the following. Suppose I start with the spin 2 field. I will show you in a moment why spin 2 field by itself coupled to T mu is not a consistent case. I mean, except as an approximation. Okay, and that essentially has to do with that. If you look at the source has to be conserved for the consistent coupling, and the source energy momentum tensor cannot be conserved on its own if it is interacting with gravity. So you say, yeah, of course that is to be expected. What you need to do is to take the energy of the spin 2 field and couple it to itself. So to the next order you do that, and then you compute the energy again and you couple it, etc. and iterate. And if you do this infinite sum, you will end up getting general. There are several claims in the literature that X has done it, Y has done it, etc. If you look at it, in every one of them at some stage, general relativity will be assumed. Features of general relativity will be assumed in one form or the other. Now it is very easy to see why it cannot be done as stated. Okay? So let me make that statement very precise. You are given Lorentz invariance and Lorentz group structure. You are given nothing about curved spacetime, but you have the entire machinery of curvilinear coordinates and coordinate transformation to curvilinear coordinates. Because after all, xy is to r theta phi is allowed. So you can think of curvilinear coordinate transformations in 4 dimensions, no problems. But you are not given the machinery of the general coordinate transformations and the general covariance. If general covariance is granted to you and you want to write down an action which is generally covariant, it is 10 seconds to write down r root minus g. You don't have to do anything. So you have to derive it without general covariance ever being assumed, and that cannot be done. Now there is a very detailed discussion of this in a paper of mine which I would like you to refer to if you are interested. But I will give you a very simple qualitative picture as to why it cannot be done. First, starting from this action, and you can compute what is known as the Belinfante canonical energy momentum tensor for the spin 2 field. Then you can couple it to HAB. Then you can compute the energy momentum tensor for that, couple that to HAB, and you can iterate that. It's trivial to see that that will never give you Einstein-Hilbert action. That is because all your iterations are power series expansion in the coupling constant L. You will get L, L square, L cubed, etc. You will never get 1 by L. A non-analytic piece will never come. Therefore, just with these lines you can prove that Einstein-Hilbert action cannot be obtained from gravitons by coupling to any kind of jugglery. What you can do is then ask the reduced question. Can I get gamma square action? Okay, after all I don't care about surface terms, I am going to take a completely particle physics perspective. I have a second rank spin 2 field. I am going to couple it to its own energy momentum tensor. I am going to iterate. Can I get the correct field equations of Einstein's theory? For that I don't care about the surface term. We will come back to it later. Again you cannot do that. That reason is more subtle. If you write down the energy momentum tensor for this, that energy momentum tensor is not gauge density. Now this is something which some of you in the GR course would have learned. Because in general relativity, there is no energy momentum tensor which you can write down for Einstein's theory, which is generally covariant. And there are very good reasons for that. Locally it cannot be defined because I can make the derivatives of the metric vanish. So there is no well-defined local energy momentum tensor for the gravitational field in Einstein's theory. Therefore, in the linear limit, if you construct any one of them, the so-called pseudo-tensors, and you take the linear Lorentz, there are several Lorentz invariant structures. If you take the linear limit of them, they will not be gauge invariant. Because we know that the general coordinate transformation goes to gauge transformations in one direction. I kept saying that that direction is perfect. It is only the reverse direction where there is a problem. So, since you cannot have such a structure, you cannot have, in fact you can formally prove that there is no energy momentum tensor built out of this spin-2 field, which is gauge invariant. So the moment you couple it to this, you find that the theory breaks the gauge invariance. What people have done, I mean, there are derivations of this which sort of goes up to a point and then say, oh well, what else can this term be? We will guess a term which we will write down, etc. Which if you know, you can do that, and it's a good interpretation, but it's not a derivation. The cleverest derivation is due to Stanley Diesel. But there, what he does is that he will change the structure of the gauge transformations as you go along. I mean, this is not the way he puts it, but this is what it effectively does. We do know that at the lowest order, x mu going to x mu plus xi mu gives you a particular gauge transformation. But that is a linear approximation in delta g mu. You can take the next order approximation. So to quadratic order in psi mu, you know how g mu should change. So you ask the second order term to be invariant under that transformation, third order term to be invariant under different transformation, etc., etc., then you can build it up. But that again you can do only if you make a correct choice for the surface term to begin with. So if you did not know Einstein's theory and you were given a spin-2 field theory with the correct equations, by coupling it to the energy momentum tensor and iterating, you will never get back Einstein's theory. You need extra structures, and it is nice to explore with different extra structures and see what you can get, but none of them are approved. So this goes on to show that there is something really special about Einstein's theory. I mean, there is more to gravity than gravitons, is the way I would like to put it.
There's also this approach by Thanu
Yes.
and others. There, apparently, they only assume that the nonlinear algebra is a deformation of the linear algebra.
The deformation of the linear algebra is equivalent to changing the gauge transformation at different stages. Once you do that, you can do that.
But there you don't assume any other.
Yeah, but that particular deformation, there are various kinds of deformations of the linear algebra beyond the leading order which is possible. One of them was picked up so as to produce Einstein's theory.
So they claim that they have the most linear.
No.
So
The point is that there is a choice which you have to make as to what this deformation should be. Okay? You can make different choices, and that is what I said. There is a fairly crazy theory I can construct out of it, which can also be written down as a deformation of a particular structure.
Typically what happens is if you put a crazy thing is that you have more degrees of freedom. Right?
That is not the issue here. The issue is purely algebraic.
Algebraic.
Yeah. The issue is whether you have a unique choice or not.
Yes, but the point is if you want to conserve the properties of the algebra that be with a certain number of generators and in a way that may kill, they may only give 2 degrees of freedom for the theory. I don't know.
No, I don't know what you're saying.
Okay, that's what they say in the article, okay? They make a BRST calculation.
I know.
Okay? And they say, okay, if we have this kind of algebra, which have the same number of...
At the linear level or non-linear level? Linear, fine, no problem.
And then they say that the only way of deforming in a way...
That is the point. When you say it is the only way of deforming, it is assuming certain BRST constraints are maintained. This turns out to be equivalent to choosing one out of many. Okay.
What I say is that what I understand is that if you don't choose this one, then you lose. For instance, you may generate new degrees of freedom, for instance.
Yeah, that is one way of generalizing. What I am saying is there are other ways of going in which you will end up getting more general structures and which you cannot bypass. See, the basic way to think about this is that you cannot couple a HAB to an energy momentum tensor unless you know what is the energy momentum tensor. Assume for a minute you have succeeded in your project. then you should be able to tell me what is the energy momentum tensor in general relativity. And we know that has not been done. Okay? That is the simplest way of thinking about it. If you are obtaining it by coupling order by order, in fact you can do the following. You take Einstein's theory, go to Mathematica or Maths Tensor, and expand the Einstein action to, let us say, up to 17 terms in HA. Rewrite those terms, and at every term you will know what the coupling is. You will find that HAB couples to a TAB at the lowest order, then it will couple to something else at the next order, and you can pick out all of them. Then you look at it, up to third order this calculation has been done. The third order calculation was done by Anthony Lazenby and his collaborators very recently. If you look at these terms, there is no way you could have guessed these terms from knowing just the spin 2 field, or by just transforming it with some gauge invariant prescription. What you can do is to say that I want this prescription to go from step n to step n plus 1, the following prescription to go from step n plus 1 to n plus 2, etc. And these prescriptions are motivated by what we know the final theory has to. So there are forks on the road where you have to make the choice. Okay. Fine. Now let me come back to this question as to what is the motivation behind this itself. The motivation has to do with the fact that if you write down this theory,
Yes, final comment.
yeah,
Well, you change these coefficients and you analyze the equations of motion
if I change which coefficient?
of the third or fourth order.
Right, you will change the field equations of
You
gravity.
find the field equation and you find in particular more degrees of freedom.
Yes, but the more degrees of freedom is less of an origin for me rather than the fact that I don't recover Einstein's field equations. The aim is not whether you can produce a theory of gravity. The aim is whether you can get Einstein's theory out of the structure. The answer is
Yes,
no.
but the point is that, so my point is the following. This kind of theories have more degrees of freedom only in the couplings, in the higher order. That means that they are solely coupled theories and you directly throw them to the rubbish.
No, I'm saying I would have thrown it into the rubbish anyway.
Because of that phenomenon.
Yeah, exactly. Right? Okay. Fine. So the statement which I am making is very precise. If you were not given general covariance as a guiding principle, and general coordinate transformation group as the group under which the theory is invariant, and you are given everything else which you know in quantum field theory, that is Lorentz group structure, whatever favorite scheme of quantization you have, BRST, whatever, and a spin 2 tensor field which satisfies the standard equations at the linear order, you cannot get G. You need to put in some extra assumption, then it is a question of choice as to which assumption looks very natural. That's all. Okay.
Let me comment. Sorry
Yeah.
to interrupt you.
Right.
Of course, this phenomenon also occurs.
Sorry?
This phenomenon also occurs in H.
Absolutely.
which are non-abelian.
Yeah.
These non-perturbative effects
Mhm.
also are invertible. That way, you also have to take them into account. Full
Okay.
theory, it's not true that you, by linearizing those theories, you
Right.
get the full.
There is one major difference. The action for a basic nonlinear gauge theory does not have a surface term. It is FAB, FAB.
Oh, you have FF dual.
No, that FF dual you can throw away if you want to. Okay? So I can live with FAB, but there is no such equivalent of FAB in general relativity. I take your point because you can add that and then there are all these topological issues, etc., which is what I meant by saying only the part which is connected to identity you can do this exponential. Now I don't even have that opt-out in Einstein's theory. Give me a Lagrangian in Einstein's theory, which is generally covariant, and it is quadratic in the first derivatives of the matrix. It doesn't exist. Now I ask you, give me a Lagrangian in a gauge theory, which is quadratic in the first derivatives of the gauge fields, and is gauge invariant. You will give me that. You will give me more than one. Okay, because there is FF and FF dual. So you can certainly give me FF. Okay? But you cannot do that in gravity. So in gravity, you are forced to take this surface term into account. In gauge theory, well, it is very nice to take the surface term into account because we know that it leads to interesting physics. But if I had not taken the surface term into account, I could have still written down my field equations. And I would have preserved all the symmetries. I agree that philosophically, that is not the way one would have liked it. But mathematically, there is a consistent procedure. Here, even purely algebraically, you cannot do that. So it's a very strong constraint that the R Rhodmann energy and its surface terms are very, very special. Not to mention the fact that it has interesting connections with, for example, thermodynamics and stuff like that. Okay, now let us go back to this theory which we wrote down and sort of take it to its logical conclusion. So if you have this and then you couple this HAB to a TAB of matter, what kind of field equations will you get? So the field equations which you get is essentially you are going to vary this and you will end up getting one more derivative on that. So let me just write it down as, let us say, dA of M ABC ijk di of H jk equals some, what are the free indices? A is gone, so TBC. So some coupling constant times T. This is the kind of field equations you will get. What is interesting is that you can prove using the form of this, it's a little bit tedious algebra but not too tedious, that the left hand side satisfies an identity dB dA of M ABC ijk di of Hjk is 0. This just comes from the symmetries of the theory. The analog in electromagnetism is that you would have got di of Fik is Jk. And we know that the left hand side satisfies the identity di dk of Fik equal to 0. Which in turn implies for you that dk of jk equals 0, which you don't bat an eyelid because you say that just means charge is conserved. So you couple to a conserved charge and electromagnetism can only couple to a conserved charge, and as long as you make sure that the charges are not created or destroyed, electromagnetism is a consistent thing. But when you plug this in here, you end up getting the constraint that dB of TBC equals 0. This is the problem, it's a well-known problem, that to the linear order, if you couple the graviton to your energy momentum tensor, it implies that that quantity has to be conserved. Now, that is not consistent with gravity affecting it, except as an approximation. As I said, you can certainly do this as an approximation. What it means is that the equations of motion for matter are contained in this equation. And this equation of motion is the same in the presence of gravity as well as in the absence of gravity. That means the matter doesn't care, matter is not affected by gravity to the lowest order. So this is not a consistent thing. And that is why people wanted to put on the right hand side some other energy momentum pseudo tensor of gravity, so that only the total thing is conserved, and then iterate and find the full theory of Einstein's theory from this, etc., etc. And I have explained to you why that doesn't work in this present context. Okay, so this is basically the part which I wanted to cover as far as the graviton is concerned. But there are some interesting curiosities, well actually more than curiosities, which comes about even at this level in the structure. So for that I need one of these equations. Let me retain this equation on top, which I want to mention. This has to do with the way matter attracts each other even at the level of linear theory, which you may think it should not hold any surprises because there is some energy density and that produces a linear order perturbation and that will affect the other matter. It turns out that there are something which are funny which happens. Firstly, suppose you take this linear theory and just to simplify maths, which I have not worked it through, you can notice that there is still one more gauge degree of freedom which is left even after we have, this is the gauge invariant construct. So I can choose my gauge degree of freedom in such a way that some of these terms can be simplified. What is usually done at this stage is to impose a gauge condition which could be, let us say, dA of HAB equal to 0. This is not absolutely essential, but this makes life easy. So we will impose this gauge condition. So in this term, if I take a total divergence out, dA will go and act on this, and once I have imposed that, I can throw away this term. So your action reduces to the form with just the other two terms, which is integral d4x half dA of h bar dv dA of h bar jj minus dA of h bar bc dA of h bar bc. It's a fairly simple structure.
I have a question.
Yeah.
Is it clear that it's okay to impose the gauge constraint inside the action?
It is not. But if you impose it on the field equations and then ask whether this action will give you that field equation, the answer turns out to be yes. Therefore, in this particular case, it is okay. In a general construct, I would be very suspicious of putting symmetries into the action by gauge conditions. So it's a good point, but it just turns out that in this particular case, I can vary this, write down the field equation, vary that, write down the field equations, and make sure that they are fun. So this action is as good as whatever action I want for this construct. Now, my purpose is again very limited. Once you have this, you can go to the Fourier space. That is, you can write down all of them, Fourier transforming in e to the ikx. Then you can get the momentum space propagator for this space, for this field. What it means is that the field equations which arises from this will have the structure, some linear operator acting on, let us say, h bar AB is equal to some source. So this is a second order differential operator. So if you go to the Fourier space, it will give you the kind of propagator structure for the thing, which you can find out. Now the propagator structure, which I will just write down from this, happens to be the following. I can write it as some, let us say, dAb ij of k. Again, I think it is 1 by 2k square with a positive sign, but it is, the correct expressions are always in the notes. Then I have a minus eta ab eta ij plus eta ai eta bj plus eta aj eta b. If I got indices wrong, we'll correct it in the end. Now what is this good for? This is good for a few things. What it tells you is that the coupling between two source distribution given by two energy momentum tensors has the structure, the coupling term will have the structure which is T AB D AB ij T ij. This could be source 2 and this could be source 1. Okay? So this is essentially the same as what we did naively by hand waving for electromagnetism. J times J is in the scalar field, Ji times Ji divided by k square is for electromagnetism. This is the structure for gravity. Obviously 1 by k square is going to give you 1 by x kind of an interaction between the distributions, and this is what it is. But we haven't made any assumptions about non-relativistic limit. This big curvature, that is all we have assumed. We haven't said anything about, so I can talk about relativistic fluids in this formalism. So how does this structure look like? So let us do the contraction. So I have an 1 by 2 k square to begin with. Then AB and IJ I had to contract. So this is going to give me the traces. So that is going to give me minus the trace of the first distribution, then the trace of the second distribution. That's correct. Then I am going to take these terms. Now you can easily see that they are going to give me the same contribution. So you will end up getting plus 2 times TAB, TA. Assuming I got everything right. Now you may be still wondering, why am I doing this? There is a very good reason. Let us say that the source which I have is some material particles. So for material particles, your TAB is dominated by T00. So TAB is essentially going to be T00. All other terms are 0, and this is given by rho. In that case, the trace is also going to be rho. Okay, this is like massive points. So what you will get here is rho, this is of course 192 and 192. So you will essentially get rho 1 of k, rho 2 of k in the Fourier space, 2 times that. Then again you will get rho 1 of k and rho 2 of k here, just once with a minus sign. So you will essentially end up getting here something which looks like rho 1 of k, rho 2 of k by k square. Give or take factors of 2. This is fine. It just tells you rho at x into rho at y upon x minus y in real space. That is how gravity acts, perfectly fine. Now take something relativistic, like a beam of light which is interacting with another beam of light, or two photons or whatever. They have zero trace for the electromagnetic thing. This is going to be given by, again, the dominant contribution, which is going to be rho. You can work this out. And then you will find that the answer is going to be twice whatever you would have got the other. So if you have relativistic particles which does not have the trace, that is, the trace is vanishing, and you compute this, and I have not worked out all the algebra for you, but if you plug it in and you work that out, you will find that for relativistic particles, the force of attraction turns out to be twice as strong as for non-relativistic particles. And this is why the bending of light is factor 2 more. And this is something which you can get at the level of gravitons. And it comes essentially from this structure, which in turn comes from this structure, which in turn comes from the gauge invariance. So given the gauge invariant spin 2 field, you can almost prove with these surface terms being thrown and that sort of stuff, you can almost prove that relativistic particles will attract each other with twice as much force as the non-relativistic particle. Okay? So that is an interesting curiosity which I want to mention. And I also wanted to connect this up with the linearized theory of gravity, doing things properly with gravity, because it is very curious how this emerges in gravity. Yeah?
I guess you can also get from here the gravito-magnetic
repulsion.
Two motions of particles.
That's correct. Yeah, I think it is there as an exercise in the course notes, but I'm not sure. Yeah, okay, you can do that also, and you can also do the photon-photon scattering by a graviton exchange, because tree level, if I have one photon with a momentum vector k1 going to k2 and a momentum vector p1 going to p2, you calculate the scattering amplitude, and you will find that if the photons are propagating in the same direction originally, 2 photons, it has a k1 dot k2, and that will vanish. So the result is the following, which I will derive after the break. If you have a laser beam of light going along one direction, and you have another parallel laser beam going in the same direction, at the linear order, they don't see each other. Which is very surprising, because normally one would have thought that at linear order, the energy densities are what matters. So the energy density of this will curve the space-time around it. Therefore, it will affect the other one. Think of one laser as very strong, producing the test field, producing the curvature, and the other one being a test laser. The test laser photons will not feel the attraction of this. Okay, I'll show you how that comes about in GR just after the break. So there, at the same time, if you reverse the directions, they do see the effect. Okay, and that also will emerge from this when you do the momentum transfers correctly. If they are traveling in opposite direction, they do attract. While if they are traveling in the same direction, it doesn't. Of course, in some sense it is nice, because if you have a very strong laser beam, you don't want one part of it do something to the other part. But this is how it works.
It is related to just what I said.
Exactly.
Magnetism.
Exactly. It is related to that repulsive force which is coming. That's all. Yeah. Okay, let me stop here and we will continue around 4:15. Will that be fine? I have given up. Yeah. Okay, so let me begin. So I want to go a little bit further with the structure which we showed here for the linear level coupling, which I rubbed off. So let me write it again. We sort of showed that the coupling term between two energy distributions essentially go as TAB of 1, TAB of 2, I did wipe it out, yeah. That's correct. 2, this is 2 times this minus T of 1, T of 2. So I want to use this to study this phenomena which I told you about, which is somewhat peculiar. You think of this chalk is study the following phenomena. You have a xy plane. This is x-axis. This is y. And I have a beam of light, let us say, going along this x-axis. This is a strong laser beam which is producing a curvature around it. Then I have another beam of light which I will call the test beam of light, which is also going in this direction, and I said that there is no force between these two. And I want to show you why, because it is interesting. So first, one way of looking at it is to look at the TAB for this. So we are talking about a beam of light which is going along the x-axis. So you can easily convince yourself that only non-zero components of that will be T00, Txx, and both will be equal to minus T0x. This essentially comes from the fact that the TAB of a beam, directed beam, is proportional to Ka Kb, where K is the 4 vector of the photons. So Ka Kb, if K is in the x direction, will only contribute these. And the signs again come because of our convention, where when you lower 2 of these zeros, nothing happens. When you lower one of them, this gives you this. With this, you have some source, and this source is going to produce the second one on this structure. I'm not saying anything about the second one, which also has a similar structure, but it is not really necessary to say something about that. So if I look at this epsilon for this, what I'm going to have, this is for, let us say, TAB of 1. So I have 2 times T. The traces of course vanish because it is electromagnetic beam. So only this term need to be computed. So I have 2 T00 acting on 00 of 2. Then I have T of 0x, T of 0x, 1 and 2, twice that, then T of xx, 1 T xx of 2. This is what we have. Okay? Now we already know that this condition holds, so this is T00 and this is going to be minus 2 times T00. Then this is going to be T00. So you can easily see that if I combine these two up with the same kind of things on the other one, that is going to vanish. Because there are 2 times this term, and that term is going to compensate for these ones. Okay? because I just pull out the other one and you will get this. Now this is assuming that I know somebody has told you that this is the coupling. And this coupling, as I told you, came out of the fact that you are sort of linearizing anti-gravitational theory and then getting a momentum space propagator and doing the contraction, etc., etc. But how does GR approach this problem? What happens in standard GR? That is a lot more interesting. In standard GR, this photon is going to follow a geodesic equation in a metric which is curved by this. So we wanted to know what is the metric produced by this source. So let me call this source as 1. And I want to ask what is the metric produced by this source. So for that we again write down the linearized equation around flat space-time, Einstein's equation linearized around the flat space-time. And that we almost got up to it, though I never wrote it down explicitly. But it will turn out to be the following. Kb is some kappa times PAV of the source. Okay. This is, if you have done a gravitational wave course in first year GR, you know this is what that equation is. The H bar and H are the same here because T bar and the T are the same because the source is traceless, it is an electromagnetic field. So I don't have to worry about this. All that I need to know is that because I have these non-zero components, the only non-zero components in H are going to be H00, H0x and HXX. And again, using the same boundary condition on all the components of the equations, I have the condition that H00 will be equal to HXX will be equal to minus H0x. This is the only information I need. Then of course if you give me this, I will solve and I will get the spatial variation and all. So how does the second beam react to this? So I have to write down the geodesic equation for the second beam. So that will be d square xi by d lambda square with some affine parameter equals minus gamma I AB dxi by d lambda, rather dxa by d lambda, and dxb by d lambda, which gives you the trajectory of the second beam of light in the space which is curved by that. We are essentially interested in knowing whether there is an acceleration in this direction. That is our point. So for xi, I only have to look at the y-axis. So I put the y here. So this becomes y. And I have to compute this. Now I first noticed that these gammas are going to be produced by the perturbations, which means these are already linear in H. And I am doing everything to linear order in H. Therefore, as far as this is concerned, I can treat as though it is in flat space. So there is already a term here which is linear order in H. So this I only need to retain at the zeroth order. Now zeroth order, when the light is going along the x-axis, dt is equal to dx. Okay, in the same direction. So this will become, in all the terms I will get a, let us say a dt by d lambda, the whole square, times, when both of these are 0, I will get gamma y 0, 0. Then I will get, in a mixed term, 2 times gamma y 0x. Then I will get gamma y xx. So let us work this out. I'll use this part. So let us look at that combination. Gamma y, gamma y 0, 0 plus 2 times gamma y 0x plus gamma y xx. This is easy to do, so this is going to be, there is a GYY term for rising each one of them. The metric gets perturbed only in the TX sector. So as far as Y is concerned, I don't care. So that is going to be gamma Y00 plus 2 times gamma Y0X plus gamma YXX. Now you write it using your usual expansion in terms of the metric. If I look at this, there is only the derivative with respect to y of these two which is going to contribute. So I am going to get dy of h00. The other two terms are d0 of 0y, and 0y is not perturbed. Then I get 2 times. In this again, I get derivative with respect to y of h0x with a minus sign. Then the remaining terms are 0 of yx and x of 0y. They are not perturbed. Similarly, in the last one, I will get minus dy of hx. Now you can see what is happening, because this h00, h0x, 2 times h0x and hxx. These two are equal to each other, so these two things together, if I wipe this out, it will give me a factor 2, and they differ from each other by just a sign. So this is 2 times this quantity goes, and this h0x is minus h00, so this whole thing is 0. So that is interesting, because without using anything about the graviton structure, by using just geodesic equation and this equation, I end up showing that there is no acceleration in this direction. Okay. Of course, it is all consistent, because I know that if I have linearized theory with a equation like this, that is same as what I would have got in the graviton picture if I write down the propagator. But that is what is not clear is this equation. What is its role in the graviton picture? So let us try to understand it correctly. In the graviton picture, I have a propagator in K space. Then I have 2 energy momentum tensors. Then I write down the interaction energy between them. What I show is that the interaction energy, because of the symmetries of the problem, just vanishes, so that they don't see each other when they are 2 parallel beams of light. Okay. Here, I don't write down an interaction energy. I just compute this. Up to this part is common, whether you are using a graviton kind of a picture, or whether tree-level scattering in graviton kind of a picture, or whether you are writing a linear perturbation around the Einstein's theory. They are identical mathematically. There are no surprises. The question is, what does this translate into? This is the equation of motion for a photon. Now, the equation of motion for the photon, how did this fact got incorporated in anything which we did? Okay, so let us just think about that. I want to make sure you understand what the problem is, because if I take Einstein's theory and linearize it around the flat space-time, I will get that equation, I will get this geodesic equation, I can do this entire calculation, convince myself that these two things do not attract each other. Then I say that if Einstein's equation is linearized around the flat space-time, I can think of it as a spin-2 field. In the Fourier space, I can think of it as some kind of gravitons which are propagating. Then I can write down the coupling between 2 energy distribution T1 and T2 using that. And then I can look at the same problem from that angle. And of course I get the same answer in both the cases to the lowest or tree-level order. But what is the translation of this, and where did this information go in the other picture? Where it goes is what that condition which I wrote down. I told you that the graviton picture, the kinetic energy term, already know that a source to which you are coupling it has 0 divergence. Okay? Because that is guaranteed by the structure. Just as the source to which electromagnetic field is coupled has 0 divergence because of the geometrical structure of the left hand side, the antisymmetry and symmetry. Because I know that, the source has to satisfy the equation dA of TAB. in this theory. Now the source satisfying an equation dA of dAB is equivalent to geodesic equation. So that is how that information is put in. The symmetries of the coefficients in the different terms, which guarantees that the source is conserved, also guarantees that in this particular case there is no attraction. That is why I spent so much of time doing that. And the symmetries you can work out in the case of Fourier space very easily, because all the derivatives are dot with k. So if I look at the J of x, the charge current, the electromagnetic current vector in the real space, the conservation of that is just ki dot ji is equal to 0 in the Fourier space. Similarly, ka dot tab is equal to 0 is the conservation of the energy momentum tensor in the Fourier space. So the propagator which you have written down guarantees that conservation, and that conservation is what leads to this equation. Okay, fine. So that essentially concludes all that I wanted to say about the linear limit. Yeah.
I don't really get the last 2 minutes. Can you summarize?
Okay. So yeah, it's a bit crooked at a point, but what I'm trying to say is the following. Take no, it is not so much as algebra as a concept. Take Einstein's theory. Linearize that theory around flat space-time. Linearize the geodesic equation around flat space-time. Consider the problem of two parallelly propagating light beams. We get the answer that one is not attracting the other. It's completely straightforward. We just did the maths and you get the answer. Now you do the following. You linearize Einstein's theory around the flat space-time. You have a spin-2 field. Then you look at the propagator structure of the spin-2 field. Then you say that the energy coupling if you want to think of a tree-level quantum theory or whatever, it is TAB of 1, TAB of 2 multiplied by this propagator. Then you look at the structure of that and you put in the TABs of the two parallel beams of light and you get exactly the same result. Now I am saying there is a slight subtlety here, because in the propagator expression it is not very clear how it contains the information contained in the geodesic equation. And I am trying to explain to you where that came from. Where it came from is that when you write down the linearized equation for the graviton, the left hand side, the linear differential operator acting on HAB, satisfies an identity. That identity comes from the symmetries of that mass matrix MABCIJK which we threw in, and that symmetry is carried forward in the propagator index symmetry. That constraint in turn implies that the TAB is covariantly conserved, and which is in the limit it is dA of TAB is equal to 0, which is equivalent to the geodesic equation. Okay, so it's a little bit of a subtle loop by which it is closed. Okay.
Sorry, and is there any experimental?
No. So, Martin was asking this. Any beam of light which we have, the strongest lasers are so weak that there is nothing which we can do to test this out. And in fact, it would be more interesting to see whether a laser light will loop onto itself. This is what you were saying, and go round and round with its own gravity or something. But you can just do an order of magnitude estimate, and you will find that the curvatures are at all invisible. It cannot be done. I mean, it cannot be done with present technology. Okay. So now I want to discuss a few more topics, in specifically two more topics, which are sort of loose ends, okay? Because it has been a spillover from the previous lecture before going over to another coherent topic, because I think these are interesting and I want to just cover them. The first thing has to do with the meaning of Einstein's equation. Normally, after you write down the action and all that and you derive it, you write the Einstein's equations as dAB equals some kappa times TAB. And the question is there some sensible way of interpreting this equation geometrically? Okay. What does this mean? Now it turns out that there is a nice sensible way of interpreting this geometrically, which is not stressed, so I'm going to spend time on that. What we are essentially trying to say is that the energy momentum tensor produces the curvature, but it doesn't quite produce the curvature. This only has, if I have written down TAB minus half GABT, left hand side only has a Ricci. It is not a full Riemann curvature. So what exactly does TAB produce? Well, it produces a fairly interesting object, and that is what I want to define. Let us start with some observer in this spacetime who has a 4-velocity ui. Now, given such an observer, you can construct a projection tensor Pij orthogonal to the world line of the observer, which would have been delta ij, and in my notation and signature it would have been ui uj with a plus sign. I'm assuming everybody knows what projection tensors are. So this is a tensor which projects any vector to a surface which is orthogonal to ui. And this itself is orthogonal to ui. If I dot it with a ui in my notation will be minus, and this will be uj, and that will be 0. Okay, so this is a tensor which is orthogonal to the ui. It lives on the hyperplane. And if you take any other vector and you dot it with that, the resulting component will also be orthogonal to ui. So it just picks out the orthogonal transverse component of any vector. Now, given this, any tensor index can be sort of projected down to this hyperplane. In particular, you can take the Riemann-Christoffel tensor, let us say R, A, B, C, D, and project each of its index orthogonal to this. So I can do PAI, PBJ, PCK, and PDL. Okay, so let me call this something. Let me call this some R, I, J, K. Now this is not the Riemann-Christoffel tensor of the orthogonal surface. I mean, those of you who know Gauss-Godowski equations will know that there are extra terms which comes from the extrinsic curvature. But this is an interesting quantity by itself. Okay, this is just the Riemann-Christoffel tensor with the component just projected onto the hyperplane. But what is it? Let us try to stare at it. In particular, I want to look at the scalar which I can build out of this. So the scalar which I can build is obtained by dotting them suitably. So let me try to do that. So from this I can get, let me write it down here, R, I'm going to do Ij, IL, and then multiplied by Gjl. Okay, so this is like a scalar curvature which I am obtaining. This is exactly how you would have got the scalar curvature from the original Riemann, by contracting on the first and the third and then contracting on the second and the fourth. So I want to do that. So here I am going to first put I and j equal. Okay, so let me write it down. This is going to be on here A, B, C, D, and let us work out the contractions. So I am going to contract I and K. So I get P, A, I, then P, K, C. I contracted on I and K. Then I am going to contract on J and L. So I get P, J, B, P, D, J. Now, of course, these are projection tensors. No, I haven't written down the contraction correctly. I said I am contracting on I and K, so this should be K. Yeah. Now, these are projection tensors. So, if I just contract two projection tensors, I get back another projection tensor. So, this is just PAC, and this is just going to be PBD. Okay. So what I am left with is R, A, B, C, D, PAC, which is GAC plus UAUC, then a PBD, which is GBD plus UB UB. Now the question is, what is this? It's actually an object which you are familiar with, except that it has never been derived in this form. So let us do all the contractions. So first there is a GAC and a GBD contraction which comes from the product of these two. That is just going to give you R, the regular scalar curvature. Then you are going to get contraction on this one with a BD. So you are contracting on B and D and dotting with these two. And similarly you are getting another one here. So that is going to be plus 2 times an RAB dotted with U. Okay. The last one will just go away because of anti-symmetry in the indices, and there are 4 of those. Now this is nothing but GAB 2 times GAB UAU. In GAB you have an RAB, RAB UAB is fine. Then I have a minus half GAB, but that minus sign is taken care of because in my norms U square is minus 1, and that half is taken care of by this factor 2, that will give you. So this is quite remarkable. I have defined R IJKL, which has a very nice physical meaning. You take the Riemann-Christoffel tensor, project it onto the spatial surface. Then you play the same game you play with the original Riemann-Christoffel tensor and you find your R. That R just turns out to be 2 times GAB UAU. So what Einstein's equations tells you is that R is equal to, in proper notation, 16 pi times rho for all observers. What is rho? Rho is just TAB UAU. So you have an observer with a 4 velocity UI, that is how we started. This observer is going to measure some energy density. The energy density he will measure is this quantity, TAB UAUB. He will also measure with the curvatures projected onto its surface, a scalar curvature. Then he will just say that the scalar curvature as measured by me is equal to 16 pi times the energy density which I have measured, and this energy density just produces that scalar curvature. This, we insist, should hold for every observer. This is equivalent to saying that GAB minus kappa TAB dotted with UA UB should be 0 for all UA and UB, all time-like UA and UB, and you can convince yourself that just knowing it for all time-like vectors UA and UB is equivalent to GAB being equal to kappa TAB. So the Einstein's equation actually has a very simple geometrical meaning, which is, I haven't seen this relation in textbooks, so that is why I spent time on that. Now there is a very nice interpretation you can give to Einstein tensor if you dot it with the 4 velocity of an observer as essentially the curvature of the Riemann-Christoffel tensor projected onto that surface. Okay? And then this is all which you have to state. For every observer this should hold, and if it has to hold for every observer, Einstein's equations has to hold.
So
Okay.
if you include a cosmological constant?
Well, that you can trivially do, because for me cosmological constant is just one particular kind of TAB.
So we see the base circle.
That is right. So you change TAB to TAB plus lambda times TAB, and that is taken care of. Just one particular kind of cosmological constant. Okay. So then there is one more thing about the geometrical aspect which I want to spend time on. This has to do with the curvature itself and the number of independent components Riemann-Christoffel tensor has. The usual way of obtaining this is to first obtain Riemann-Christoffel tensor, look at all its symmetries, and do the combinatorics, and you will find that, for example, in 4 dimensions there are 20 components. But what does this mean? What does it physically mean? Because curvature is the central quantity in this. And I want to give you a completely different alternate way of arriving at the same number. Okay? To do that, we want to know what the curvature is all about and how many components it has. So we will try to eliminate curvature. So let us take some space-time and let us go near some event, and at that event we were given some coordinate system xi with some metric, their derivatives, etc. What I want to do is to think of a coordinate transformation to another set of coordinates, let me call it x bar I from xi, which I Taylor expand around that event with some coefficients, let me call this bik xk in the original coordinates plus ci jk xj xk plus di jkl xj xk xl. Turns out this is sufficient for our purpose. So what is being done is that you have one set of coordinates xi and I have a coordinate system, and then I make a coordinate transformation around, let us arbitrarily take the point to be at the origin. Originally xi was 0 there. Then I go to the near that point and I don't shift it around, so I again keep it as origin. And then I make the transformation which I Taylor expand in terms of the old coordinate system. So if you want to, you can think of some function which is just Taylor expanded in x. Okay? These are the coefficients. So I can choose all these coefficients at any given point. Now I want to choose them in order to do the following things. First I want to make GAB go to eta AB at that point by choosing my B. Then I want to choose C's in such a way that di of GAB vanish at that point, and I want to know whether I can do that. Then I want to make the second derivatives of the metric, di of dj vanish at that point, and I want to know whether I can do that, etc. Okay, we'll find that already we are going to run into trouble, but running into trouble and seeing what kind of trouble it creates will tell us something. So we just have to count the number of degrees of freedom in each one of them and look at that. So, and it is nice to do this in n dimension, so I will do this in some arbitrary n dimension. Now GAB going to eta AB is a question of how many constraints there are, is the first question. So and how many terms I have here. Here this is I and j can go n values each. So in B, I have a total of n square coefficients at my disposal, where n is the dimension of the space-time. And I have to set GAB equals this. So this is a symmetric tensor. So it has half of n into n plus 1 components in n dimension. So for example, in 4 dimensions it is 5 into 2, which is 10 components with it. So if you do this, you find that the n square minus half n square gives you another half n, so it is half n into n minus 1. So not only that BIK has sufficient number to set these things to 0, I have this much extra. Okay? And this much extra has an extremely simple physical meaning. The point is that once you have done this, you have made at that point the metric to be eta AB. But we know that a metric which is eta AB is invariant under Lorentz transformations. So in D dimension, I can have Lorentz transformations which are rotations in different planes, and you can choose n into n minus 1 ways of that. This is NC2. So there are NC2 planes in which you can do Lorentz transformations and ordinary rotations. So you can take Tx kind of things being Lorentz transformations with a complex rotation factor, and xy kind of things which are regular rotation, and that freedom you are still left with. So this is just giving you that freedom. So that is fun. You can do this. Okay. Now let us look at this. Again, we count how many degrees of freedom we have in C, for example. So in C, I can take n values, and then this is symmetric, so that is this into half n into n plus 1. And I have to use that to set this equal to 0. Interesting, it is exactly matched. Here this can take n values and this is symmetric, so you get precisely that quantity. So this is 0. So you have nothing to spare with. So you can make this vanish. You have this much of Lorentz rotation which is left. You can make all the derivatives of GAB vanish, but you still have only the Lorentz group's freedom left. You don't get any extra freedom out of that, which is interesting. So this is also fine. Now let us do the last one. The last one we will find that we cannot really do all of that, so I will do this in a reverse direction. So let us take D. What constraint D is going to give? So first, how many conditions of this? This is symmetric in this and symmetric in this. So I am going to have half n into n plus 1 whole square I need this many conditions, and you will find that I don't have that many degrees of freedom here. So how many degrees of freedom I have? There is n degrees of freedom in I, and then I have to count how many degrees of freedom this has. This is a completely symmetric tensor, completely symmetric third rank tensor in n dimensions. That will have n plus 3 minus 1 C3 degrees of freedom. I'm not sure everybody knows that, so let me derive that for you. The statement is that if you take a kth rank tensor, kth rank completely symmetric tensor in n dimension has n plus k minus 1, assuming I got it right, ck degrees of freedom. So how do you prove that? Well, there are several ways of doing this. This is what I was asking you at lunchtime, so it's probably not done in tensor courses, so let me just run over the proof. I will just give you the steps. To think about what exactly you mean by saying this is completely symmetric. Okay? What it means is that if I tell you, so I'm looking at a kth rank object, so there are k indices here, and suppose and each index has to be 0, 1, 2, 3 up to n minus 1, right? And let us think of it as some 1 to n for simplicity. So if I tell you that any given component has n1 ones, it has n2 twos, nn n's in it. Of course it has to be 0 to n minus 1, but this is easier to write. With the condition that summation over ni is k. If I give you this distribution, I am through because of symmetry. I don't have to tell you where the zeros occur, where 2's occur, where 3's occur. That doesn't matter. I can shuffle them around. It is completely anti-symmetric. So the component is completely specified. Every independent component is completely specified by giving this set of integers. Okay? What does that mean? That maps to another problem which I am sure you have done in statistical mechanics. If you think of n levels, this is 1, 2, n levels. Now, in the first level, you put n1 balls. This is n1 objects here. In the second level, you put n2 objects. So you have total of some k objects and you want to put them like this. And how many different ways you can do that. Okay? This is just a partitioning problem. You take all these balls, then you put partitions in between, and then you can shuffle the partitions as well as the balls. So the number of partitions you need is n minus 1. So that n minus 1 you can shuffle among themselves in n minus 1 factorial ways. Then there are k objects that you can shuffle in k factorial ways. So total you have n minus 1 plus k object, partitions plus object. Out of this you have interior shuffling of n minus 1 factorial, k factorial. So this is your answer. This is just your n plus k minus 1 ck. Okay. So this is how you get this result. What we need is to write it down for this particular case. So this is n plus 2 c3, which is n plus 2 c3. So that is n plus 2 n plus 1 n divided by 3 factorial, which is 6. Okay, this is the remaining factors. So let us try to simplify this. So this is 4, that is 3 by 12, and this is 6 is 2 by 12. So this is 1 by 12. Then I have an n square common. There's an n square here and there's an n square here. Then I have an n plus 1 also common. N plus 1 times n square and n plus 1 is taken, so it is 3 into n plus 1 minus n square is taken, n plus 1 is taken, 2 into n plus 2. So this is 3n minus 2n, that is n, 3 minus 4, n minus 1. N minus 1 into n plus 1 will give me n square minus 2. So 1 by 12 n square into n square minus 2. Which incidentally proves that numbers of the form n square into n square minus 1 is always divisible by 12. It is anyway trivial to prove otherwise. So you have this as the total number of independent components which you cannot reduce to 0. So having done the math, let's get back to this. Up to this point we were okay. Then when it came to D, I wrote down the number of restrictions I have here. Then I subtracted from it the number of conditions which I can impose. So I did that. And I found that I fall short by this much. Now if you put n is equal to 4, you will get this to reduce to 1 by 12 into 16 into 15, which will nicely give you your magical figure of 20. So there are 20 second derivatives of the metric tensor which you cannot put to 0 at any given point after you do all. And that is why curvature should have 20 and not more than 20 degrees of freedom. So the symmetries of the curvature, I don't care how it comes about, it has to adjust itself that this matches, because this comes from plain basic combination of the coordinate transformation. Now this is quite powerful because in fact you can do a lot more complicated combinatorics and you can also understand aspects of Bianchi identity by the same method, because you just have to go one step further. Then you talk about if you have a third derivative of the metric tensor, how many of them you can set to 0, etc. But it doesn't seem to lead to anything new and innovative, but it is a nice way of seeing this. Okay. So this explains to you in a nitty-gritty way that if you are given a space-time and you try to fool around with it, this is the minimum you can do, and that is what gives you this extra constraint. Okay, so now I'm really running out of time, but let's see. We'll go on till 5:30 and stuff. Fine. The last topic which I wanted to take up is what in the notes I have just called it a case study. So the idea behind this, as I was explaining even earlier, is that there are topics in general relativity which people have looked at for years and have missed things. I mean, it's just because it is a very rich subject. So as far as students are concerned, never be put off by the issue that, oh, this must have been seen, or this must have been studied. And there are lots of times you will find surprise that it has not been studied. Yeah.
Can you just say again what we just proved?
What we just proved?
Well,
Okay, fine. What I did was, let us assume that I know nothing about curvature tensors and stuff like that. I'm given a curved spacetime with some metric. Now, I want to go to some point and I want to say that, look, I don't like curved spacetime, I want to make it as flat as possible around this point. So you have given me some coordinate system in which the metric looks horrible, but that could just be because you chose a crazy coordinate system. So let me see how best I can do that. So I choose a coordinate transformation, and then I want to see how many degrees of freedom I have in hand. So I use Taylor expansion as a trick for that.
Yeah, that's right. But what makes the second derivative special?
Oh, it doesn't make anything special. What I'm saying is, at the first derivative level, we were in excess. And we knew exactly how much extra degrees of freedom we have. That is because of the Lorentz transformation. We broke even at the next level. At the first derivative level here, we found that we exactly match. We have no extra symmetries. By the time you went to second derivatives, you already find that I cannot set all the derivatives to 0.
Yes.
Right? Therefore, I give up hope at that point and say that this curved spacetime should be characterized at the lowest order by the 20 components which involve the second derivatives.
Okay. And then the next order?
Next order would be the derivatives of whatever is characterizing this.
And does that have a...
Yeah, so you're asking whether there is something new which comes up? Yes, it does, because you can understand the structure of Bianchi identities from that. Okay? But there is a lot more combinatorics which I am not going to do, but I can tell you roughly what happens. Suppose you are given a structure, the Bianchi identities can be written entirely in terms of these Christoffel symbols in a particular combination of line. Then you ask, what is the condition that this comes from a metric? Okay? Which is a question of integrability condition for these equations. It turns out that it is the Bianchi identity has to be satisfied. That is, if you give me a curvature tensor, Riemann-Christoffel tensor, and ask what is the condition that it comes from a metric, if the Riemann-Christoffel tensor satisfies the Bianchi identity, then there is a metric from which I can obtain it. So if you give me these 20 independent functions, okay, and in some coordinate system, and you just tell me that, oh, this is coming from some metric, find the metric. In general, I won't be able to find a metric because you could have given me some crazy functions. Okay, because the metric has only 10 degrees of freedom. You have given me 20 of these objects, and there is no reason that it should come about. But if those functions satisfy the Bianchi identity, then there is a theorem which tells you that there is a metric from which this curvature can evolve. So any further derivatives can be expressed in terms of the derivatives which characterize here itself, and that is your curvature tensor. And that is why here is a good place to stop. Yeah.
I think a good example of this is the Riemann-Norman coordinates.
Yes.
There
Yes.
you can see exactly what
That's correct. Because if you take, in fact, this is the Riemann-Norman coordinates. If you take this coordinate transformation and you choose your z so that EGAB goes to eta AB, choose your b so that the derivatives vanish. If you just stop there, what you have got is a local inertial frame, which is the standard textbook result. Then you say, no, I can do still better, because in the next order, I can make sure that all the non-trivial things which I can, all the trivial things which I can set to 0, I'm going to set to 0. Then you will find that the metric can be expressed in terms of eta AB plus Riemann-Christoffel tensor multiplied by a quadratic expression in excess. And that is the minimum which you can do. And that is the construction of Riemann-Norman coordinates. Yeah, that is another way of seeing this. Right. Now I want to take up a topic which, as I said, is something which people have looked at for ages, but there are interesting things which one could still do. So that is why I called it a case study, and I want to explain the logic behind it. The problem I want to address is what is the electromagnetic field of a charged particle which is sitting quietly in a given gravitational field. For example, I can take a short scale metric and put a charge on the table. The short scale metric of Earth is good enough. I put a charge on the table and I ask what are the electric field lines which look like, which means I have to solve the Maxwell's equations in a curved geometry. I simplify the problem by saying I am going to look at a simpler case where the gravitational field is weak, and to the lowest order I am going to approximate by a Rindler metric. So I want to know what is the electromagnetic field of a charged particle which is at rest in the Rindler metric. Now why do I want to do that? Well, the reason people have looked at it is something which is called one of those perennial questions in general relativity. Every year you will have 4 papers discussing whether a uniformly accelerated charged particle will radiate. I am not even go into that issue in this course. The problem comes, uniformly accelerated particle does radiate. The problem comes because its radiation reaction vanishes, so there has been a lot of confusion in the literature. Then people misapply principle of equivalence. Uniformly accelerated charge motion and putting a charged particle on the table should be the same, so a charged particle on the table should radiate, etc., etc. I'm not going to discuss any of that. But I want to show you that you still need to look at charged particle in a Rindler frame for a very nice physical result. And I want to first describe that result, because this is there in an old paper. And then I wanted to apply that for some interesting cases in the weak gravity. Go back to your electrodynamics, where you were asked to find what is the electromagnetic field of a charged particle which is moving with a uniform velocity. How will you do that? Well, you will sit on top of the charge, and in that frame it is just Coulomb field. Then you do a Lorentz transformation. Because you know how to write down Maxwell's equation in any frame of reference. You can do the Lorentz transformation and you get the charged particle function. But then, after a few chapters, the same textbook will discuss the electromagnetic field of an arbitrarily moving charged particle, which is called an arbitrary charge potential. There they take a completely different approach, which has always bothered me. The right way to do this is, you are given a charged particle trajectory, you choose a coordinate system in which that charged particle is at rest. When you make that coordinate transformation, your metric will look horrible, but we know how to write down Maxwell's equation in a generally covariant way. So you have a new metric which is time dependent in general, but your field, the charge is quietly sitting at one point, charge is not moving. Then you solve for the electromagnetic field in that frame and you transform back, and you should get back Lennard-Weichert potential. It's very interesting because in the Lennard-Weichert potentials, all the non-trivial time dependence and radiation comes because the charge is moving. Now you view the same thing in the frame in which the charge is at rest. The charge is not moving at all, but it better emits radiation. It emits radiation because metric is changing in time. Okay? So this is an interesting transformation between these two. So I wanted to do this. And in particular, I wanted to understand where the radiation reaction comes from for this charge particle. Now I'll tell you how this project can be completed. I won't go into the detail, but it turns out that this whole thing can be done and you get an interesting result. How you do this is the following. We are talking about a charge, first of all we are talking about flat space-time physics, so the charge particles are moving in flat space-time. So this is x and this is t. Okay? Now think of a charge particle which is going on some crazy trajectory. Well, it's not superluminal, but it is moving on some crazy trajectory. Now I want to know what is the electromagnetic field produced by this charge. Now what do I know? First thing I know is that the equation satisfied by this system is box AI is equal to Ji, where Ji is at most involves the velocity of the charge particle but not acceleration because it is rho times u. From this I also know that AI is given by AI at x is given by an integral over Ji at y times a Green's function at x minus y d4y. Okay, so this is the integral which I have to evaluate. I know that this Green's function goes as delta of s square. So the propagation is along the 45 degree. So I already know that if I take, let us say, the field at this point, and I draw the 45-degree line cutting it here. It is only the properties of the charge at this point which is going to determine the field. So I am given this trajectory and I am going to find the field at this point. I only need to find the field at one arbitrary point and I know the field at given. So the field at this point, I draw a 45-degree line and I ask what are the properties of the charge here which are relevant for the field. That is also easy to obtain. If I take one more derivative here, I can write f box of Fik is dk of ji minus di of j. This equation has the same structure as this, so I could have written down the solution directly for Fik. People don't do it, but it can be done. So on the right hand side, I have derivative of j. J at most has velocity. So this at most has acceleration, but no further derivatives. Therefore, the field at this point for an arbitrarily moving charge particle can be determined if I know the position, velocity and acceleration at this point. I don't need to know the derivative of the acceleration. Then I am in business. All that I have to do is, this is the charge which I want to find. I now take another charge and I put it in a trajectory which is a hyperbolic trajectory which just goes like this. Okay? So the second charge has the same position, same velocity and same axis. Velocity is trivial. One Lorentz transformation will take care of the velocity. So you can always look at the field at the instantaneous rest prime of the charge. At the retarded time, assume the charge is at rest. So that is trivial. So you assume that the position is matching and then the acceleration is matching. Position is also trivial because I have translation of the frames which I can do. I can always choose in such a way, once this has been given to me, that the field point is at the origin of my coordinate system. The source point is at the origin of my coordinate system and that its velocity is vertical. It is instantaneously at rest. This much I can do by translating the coordinate system and making a Lorentz transformation. Then all that remains is the acceleration. Now I replace this charge, not replace, I add another charge, let us say, which is uniformly accelerating and its acceleration, position and velocity matches the charge I am interested in. Then I figure out the fields of this. Okay? If I know that, then I know the fields of the original one because they have to be identical. So the idea is that if I know the electromagnetic field of a charge which is moving along a uniformly accelerated trajectory, there is a way in which I can construct the electromagnetic field of an arbitrarily moving charge because of this construction. This also gives you another very interesting insight which I just mentioned, I won't work it out. What about the radiation reaction? The reason radiation reaction comes about is that in order to figure out radiation reaction, one has to work at one level higher. Then it turns out that you have to take one Rindler observer or one Rindler charge. Rindler charge is a charge which is at rest in the instantaneous Rindler frame. And at the next instant you have to match it to another Rindler charge because the acceleration has changed slightly. The mismatch between these two is what leads to the radiation reaction. You can show that. Therefore, the radiation reaction will have to the lowest order time derivative of the acceleration appearing in it. In the conventional way of deriving radiation reaction, at least to me, it was never clear why first derivative of the acceleration appears. It never appears in any other physics problem. And the reason it appears is that the charge is constantly trying to adjust its Coulomb field and the radiation field when the acceleration is changing. And the mismatch between these two is equivalent to the fields computed in two Rindler frames with accelerations AI and AI plus delta AI. And that difference is the back reaction which is acting on this. Okay. So this is one motivation to look at the electromagnetic field in a Rindler frame. And I wanted to give you some of the results which comes about when you do that. So as far as the metric is concerned, we will work with what has been already done in the first lecture, but I will use the coordinates slightly differently. And also for this lecture I am going to flip the signature because I am using the results from a paper of mine in which I used a different signature. So it is easier for me not to go wrong if I do that. So I use a metric which is of this form, dt square minus dx square. This comes from the standard frame by the following transformations. 1 plus g times the inertial gx is 1 plus gx cos h of gt, and g times capital T is 1 plus gx sin h of gt. And the trajectory of the charge arising out of these two is 1 plus gx the whole square minus g square t square is 1 plus gx g small x the whole square. So if small x is equal to 0 and this is 1, at t is equal to 0, x is also equal to 0. So the charge particle is, previously we used to draw the charge particle lines like this, as a hyperbola like this with 45-degree lines, and it sort of symmetrical like this. Now we have shifted the coordinate system so that the coordinates are like this. So this is x and this is t in this notation. The previous metric would have had just some g x bar here. So it would have been g square, some x bar square, and x bar square is related to this by a shift. So this is the frame I have. Now the question is, how do I define electromagnetic fields in this frame? So there are different ways of defining the electromagnetic field, and one natural way is to say that we will be interested in the forces which is acting on the charges. So the natural way of defining this is to actually look at the acceleration of a charge particle. So the equation for the acceleration would be something like uj dj of u1. This is the acceleration, will be equal to some q by m times f ik uk. So this allows you to define the electric field in a very natural way. You introduce a 4-vector EI, which is by definition FIK UK. Obviously, given an FIK, you cannot define an electric field unless you know who is the observer. And this you can't do even in flat space-time. The electric fields are not even Lorentz invariant quantities. But given a UK, you can do this. And given this, you can also define a magnetic field. Let me just give you the expression for that. Magnetic field is BK, let us say, half epsilon K ABC UA FBC. And you can again convince yourself that if you go to the rest prime of this charge particle, then things match out. This will give you the electric field, and the rest prime, this A is going to be 0, and then you will find that these three has to be special components, and special component of this with BC will give you the magnetic field, and only remaining component will stay. Okay? And this is also nice in the sense that the electric field tensor Fik itself can be reconstructed out of that. That is important. So it contains exactly the same amount of information. You can write Fij as Ui Ej minus Uj Ei plus epsilon Ij KL UKB. You might have naively thought A and A together gives you 8 degrees of freedom. That is not the case, because you can verify that they both are orthogonal to U, because Ui dot Ei or Ui dot Vk will go away. So that takes away 2 degrees of freedom. and you are left with exactly the same degrees of freedom. So this is very nice. I mean, this is not unique. You can choose different decompositions, but this is one decomposition which you can work with. So once you have given that, then you can run through the whole thing, write down the equations, the field equations in terms of them, solve, and find the electrostatic field. So the charged particle is just sitting quietly at rest in the Rindler frame. So it is purely an electrostatic field, and you can write down what the AK is. Now this has been done in literature, and people have written down the expression for that. And in fact, let me write down the expression. No, actually I won't. The expression is there in the notes, and you will find that the expression is fairly horrible. Okay? But there is a very simple way of understanding that expression, which is what I want to do. In order to do that, let us ask what is happening for the in the case of standard Leonard-Weichart potentials. In the case of the standard Leonard-Weichart potentials, you are solving for a vector, let us say A I, which is an integral over d4y. This is at some point x. It is integral over d4y, g of x minus y, times a source ji of y. Now if you are thinking of a charged particle which is moving along some trajectory, then ji is going to be an integral over the proper time, d tau, q, ui of tau, Dirac delta function of y minus z of tau, where z of tau is the trajectory. Okay? And we also know that this g is essentially going to be delta of s square, where s square is the proper interval between these two, with the factors which I have ignored, and an understanding that out of the two roots you choose the retarded solution. So if you plug this into that, the integral is trivial because you have a delta function integration over that y, because this is y of this z. So you will find that this is essentially given by, we should use proportionality, integral over d tau, delta of s square times ui of tau. Everything else will go away. This is from minus infinity plus infinity. Okay. This you can write as deta by ds square into d of s square. So the Dirac delta function integration can be immediately carried out, and you will find that this is equal to ui, and this can be written as ds square by d tau. Whole thing evaluated at the retarded time. This is just Leonard-Weichart potentials. If you think of s square as x minus z the whole square, when you take the derivative of that, you will get an x minus zi times the velocity, that ui times ri is the way you would have studied it in your standard course. But it is trivial, you can just do it like this. But what is more interesting is that this quantity has a very simple physical meaning. This quantity happens to be the affine distance along the null ray which connects the source point to the field point. But you don't need it in flat space time at all, because that just happens to be t. Okay? So if you have a static source, all that you are going to get is something like a0 going as u0 is 1 divided by the affine distance, which is t to the retarded time. But t to the retarded time is nothing but r to the retarded time. So you get a potential which goes as this if a charge is at rest. It's known as Coulomb field. Okay? So you don't have to be sophisticated about it. But it comes in handy when you do it in curved spacetime. So in a curvilinear coordinates or in curved spacetime, what you can do is that you can look at the following object. You can look at the dot product AI, yeah, this is fine, AI UI, which will go as, I have forgotten to put a charge there, but there is a charge Q, UI is 1, divided by the affine distance between the field and the source. Now there is just one bit of trickery which is involved in this, which is in this dot product. If you go back to our picture, what we are doing is the following. You have the charge, you have a field point F where you want the field, and you have drawn your 45-degree line, and this is your source point. The velocity vector is sitting here. This is UI. And you want the vector potential somewhere here. This is AI. And I want to do UI AI dot product. Now, this is not allowed in curved spacetime unless you parallel transport it. But then the parallel transport will not be unique, so you cannot do that. But in flat spacetime, in any coordinate system, I don't care. I will just parallel transport it along any curve I like, but that is unique. So there is a parallel transported vector here, and then I can take the dot product. Therefore, in flat spacetime, under arbitrary coordinate transformation, this expression is generally covariant. It is generally covariant in flat spacetime. That is, you can write it down in any coordinate system you like as long as you are in flat spacetime. Therefore, in the Rindler frame, where your UI is just one component, the A0 in the Rindler frame, the potential A0 is just Q divided by the affine distance between the source point and the field point of a light beam which goes from the source to the field. Okay. Now, just to see the economy of this expression, I will now write down the actual result in this case. If you do that, you get 1 plus gx plus half g square r square. R is defined as though it is a Cartesian coordinate system. 1 plus gx plus 1/4 g square r square to the power half. So this is the way usually it is given in papers. This is a very well studied problem, and people have all tried this by actually working out the vector potential in inertial frame and coordinate transforming. But if you just look at this lambda, you can write down the expression for this affine parameter by looking at null geodesics in the Rindler frame, and it turns out they are equivalent. And this is much more easier to understand. Actually, it gets a little better. So in order to do this affine parameter and a trajectory, you need to know what are the null geodesics in the Rindler frame. Okay. So I just want to give you a result on that, and then I want to quote one more result, which I unfortunately don't have time to derive, and then we will wind up for the day. Okay. The first result is, suppose I have the Rindler frame, and let me try to draw this in some particular way. I'll use the following picture now. This is x-axis, and this is just spatial coordinates. This is y, and the charge is at some point. Let me use x bar. So the charge is going to sit at x bar is equal to 1 by g. Okay, that is in the metric I had either x is equal to 0 or x bar is equal to 1 by g, where the charge can be located, and this is I am using x bar. So here is where the charge is, and I want to look at the electric fields. So for that I want to know what is the affine distance if I send a beam of light in some direction and it goes to another point. What is the path taken by the beam of light? So this is a uniformly accelerated frame, and acceleration in this direction, which is equivalent to a weak gravitational field in this direction. Actually think of it like this room. You have the floor, and this is it, and the x is the vertical distance. Okay. It turns out remarkably, and I wish I have a simple proof for that, I don't have, but when you work it out, it turns out that the trajectories of light in the space-time are circles. Okay. The path of the light rays in this time are things like, they go like this. Their centers are always on this, and if you take some other path, it will be like this. Depending on your initial condition, they are always circles. So the equations to these things are always x bar square plus some y minus y naught the whole square equals something like a radius, which is energy upon the y component of the momentum, initial momentum, times g the whole square. So it can have different radii, can span out like this, but they are always circles. There is one way of thinking about that is if you look at that metric which I wrote down and you pull out the g square x square factor, the two-dimensional metric happens to be what is known as a Poincare half plane. And the geodesics in the Poincare half plane are known to be circles, so it's not a surprise in that sense. But then it is a surprise that Poincare half plane has circles as their geodesics, which I don't know a simple way of saying it. But if you know that, you can convince yourself that this is what will happen. So this is what you get. Then you can measure the affine distance along this, and if you want to know the field here, you can measure that. Okay? And you can write down the expression for that. Now I will come to the most remarkable result, which, as I said, unfortunately I don't have time to derive the whole thing, but it is there in the answer. Let us perform the following experiment. You have this is there, this is G, and from the ceiling I am going to hand two charge particles. Okay, so these are two charge particles, Q1 and Q2. We can do this in this lab. Now I want to know what is the force of attraction or repulsion between these two charges. Assume they are like charges, so there is a force of repulsion, and I want to know what it is. If you ignore the fact that it is in a gravitational field, then you will say that the force is essentially going to be in these directions. So there is a force in this and force in this, and of course the tension will adjust itself and it will go in this. Resnick and Halliday problem. But then you realize that when you are doing it in curved space-time, this is not quite correct. As long as this is what it is, if you take the electrostatic force of this on this and this on this and add them up, total force vanishes. Okay, it is exactly balanced in both directions. But then if you look at the electric field lines of this, they are going to be in the curved space-time or in this accelerated frame, and you have to solve using that equation. I mean, this is the vector potential, then you have to take the gradient of that to get the electric field. You can do that. Then you find another remarkable result, which is not really relevant for this, but let me mention it. The electric field lines turns to be identical to these. So the field lines curve in the weak gravitational field exactly like the light beam. So it is as though you have a charged particle. Of course, it is true in flat space-time with inertial coordinate. If I have a charged particle, the field lines are straight lines, radiating out. So if it is emitting photons from there, they will all go in straight line. But here also it turns out to be true. You put a charge on a table, if it is emitting light, then the light will bend like this, and the field lines will also bend exactly like this. But the crucial point is that the field lines are going to bend. So if you take the field line from this, it will go like this, and the field line from this will go like this. Now you are in for something interesting. Because of this weak gravitational field, the electric field here has a component in this direction and a component in this direction. This has a component in this direction and a component in this direction. When you add up the two, these two will cancel, but there is going to be a net force because of this downward direction. And when you do that, you find that F12, in fact it works for Fij, F12 plus F21 turns out to be equal to Q1, Q2 upon C square L G. This I find remarkable. What does it mean? It turns Q1, Q2 by L, well, L is this distance between the two. Q1, Q2 by L is the electrostatic potential energy of this configuration. in a weak gravitational field. Because if you take E square over 8 pi and integrate all over for 2 point charges, you will essentially get Q1, Q2 by R. Okay, you can work that out, except for self-interaction divergences. So this is like the effective mass. So this is M electromagnetic G. So this is E by C square times G. So when you hang this thing in the gravitational field, and if you measure the tensions on these tensions has to be slightly higher to support the entire weight of the electrostatic field with the charges constant. So the net force exerted by one on the other picks up exactly this factor. Okay? Now you may think, yeah, that is very nice and very interesting, but may not be of much practical utility. It is of great practical utility. This is what you call radiation. Here is a force, so if I take the corresponding electric field of one on the other, that will go as Q by C square R G. Here is a force which is proportional to the axial field, which is proportional to the acceleration, and falls inversely first power of the distance from the point from where you measure this. You transform this extra force to the Lorentz frame, because this is all done in accelerated frame. Then you can show that to the lowest order, you reproduce exactly the radiation. Okay? There are some subtleties, because here I have taken L and G to be orthogonal direction, so it is L dot G is 0, so it will translate back. But if you take one electric charge here and one charge here, then L dot G may not exactly match. Then you have to get exactly the transverse acceleration in the radiation. Because in the radiation field it is not G, it is the G transverse. And you find that you pick up exactly that. The terms adjust themselves. So what is happening physically is the following. If I have one charge particle and I have a test charge in the back of the mind, because in the local accelerating frame, the electrostatic energy has to be supported by the gravitational field. There is an extra force which has to come up, which is proportional to that gravitational field, and it has to scale as the electrostatic energy which goes as 1 by r. This has to happen in the accelerated frame for consistency. In the inertial frame, we don't care about any gravitational fields or any such thing, we are just accelerating. There has to be an extra term in the Leonard force field which is proportional to the acceleration and inversely proportional to distance. This, I think, is the simplest explanation I know as to why when a charged particle is accelerating, it produces a term which is proportional to the acceleration and inversely falling as distance. Because in the local rest frame, it is constantly trying to support the weight of the electrostatic energy. And as I said, this whole thing can be worked out completely rigorously and done to the linear order, etc., etc. It also works to all orders. You can get the exact Lena without potential and interpret the radiation term by this procedure, but that is a lot more complicated. I think that's a good time to stop. Thank you. So is there any questions on this part, or people are too tired? Yeah.
Just a quick one.
Yeah.
So you can do this the other way around and say the relation that the electric field creates somehow gravitational.
That I don't know how to do that. I mean, no, because I have a charged particle which is accelerating. That produces, somebody has to accelerate it. That has to come externally, and it could be an electromagnetic source, but I don't care. But it doesn't produce the gravitational field. What it does is that if you take a charge and you try to accelerate it, there is an electrostatic energy associated with it, which has to be supported in the accelerated frame where you see a weak gravitational field. And the fact that in the weak gravitational field, the energy which you have to support is Q1, Q2 upon C square Lg. With insight, you could almost written it down by inspection. You could have said that this is the gravitational potential energy, so this is the equivalent mass. In some sense, it is principle of equivalence again. This is the effective mass of this energy, and mg should be the extra force. So there has to be this extra force term, which when you translate into the Lorentz frame has to appear as a force which behaves like this. But as I said, there are a few subtleties which takes care of themselves, but it is not apparent in this thing. A main thing being the transverse acceleration. That the radiation force, the standard Lena radiation field, to the lowest order is not q acceleration by c square r, it is q a transverse by c square r. So that is sort of not clear here when I keep the two charges at the same level. But when you keep it at different levels, you have to redo the calculation and you find that it actually matches and it comes out. So the interpretation is correct, but it is more non-trivial.